So hi, our project is on a paper which was inverse kinematic analysis of 6R robo using Groebner Base method, and I'm just trying to introduce it. So we had two types of methods that we usually use for inverse kinematic analysis, which is the numerical method where we try to minimize the cost function, which is usually the vector loop equation, and then we have the analytical techniques. Like for the analytical techniques, we learned Crane and Duffy's method, which uses a 32-degree, which finally drops down to a 32-degree equation for the 6R robo, and Tsai and Morgan use polynomial continuation to prove that there are only 16 solutions for any general 6R robo, and you'll basically only get 16 solutions as opposed to 32 in Crane and Duffy. Lee and Leung built up on Tsai and Morgan's function by saying that you can derive 14 equations which are devoid of one joint angle, and then you can avoid the introduction of extraneous roots like we did by trigonometric identities and such, and finally use Sylvester's method. The problem in using Sylvester's method, like we saw, was that if the number of solutions that we need is not equal to the degree of the polynomial we get to solve it, we will not get an equation that is devoid of all the roots. So you will have to keep performing or iterating through it and use various identities to finally get one equation that you can actually solve. So now Kritika will explain the investment.
So this is the method proposed by the author. Here we have shown an inverse kinematic analysis of a general 6R serial mechanism. The picture there shows 6R closed loop mechanism in which the parameters we have taken here are the A's as the joint axis, the Q's as the link vectors, the S's are the joint offsets, and P's link lengths, and A's are the twist angles, and theta are the joint angles. We have taken the normal vector loop equation, but in this case we have split it up into two parts, SOC of A and B, but they add up to be 0. And then you project the vector loop equation into different vectors like A2, A4, and so on. So we get 6 equations. In this, the left-hand side is devoid of theta 3 because the SOC of A does not include the joint axis, the joint 3. So
what's SOC?
Serial open chain A.
Serial open chain.
The part A does not contain the link, the joint 3, so it is divided theta 3. So now we need to expand the RHS to eliminate theta 3, for which we expanded the RHS, and from the first two equations, the theta 3 there is actually sine theta 3. So we are eliminating the theta 3 by equating both the equations. And similarly, from the fourth and the fifth equation, we eliminate the cos theta 3. And similarly, we manipulate these equations and eliminate theta 3 completely. This is the expanded form of the 4 equations. This we expand. We did this using MATLAB program. We expanded all those, and we got a big equation in terms of K's, where the K's are the constant mechanism parameters, which we get, and the unknown angles are in terms of the sines and cos. Here we're substituting the sine and the cos of each angle as u, v, w, and x, y, z's for theta 1, 5, and 6. So we get the 7 equations. The last 3 equations we generated are just the trigonometric identities, cos square plus sine square equal to 1. And the first 4 is how we generated. Now, solving these equations, we use a special method called Groebner Bases, which will be explained by Akash.
Thank you. Now first we'll start up with what that Groebner basis actually is. A Groebner basis is a set of multivariate polynomials which has all the desirable algorithmic properties. Now it is very easy to convert a set of polynomials of any given base into a Groebner basis. Now the Groebner basis actually comprises of all the familiar techniques, the Gaussian elimination, the Euclidean algorithm, and the simplex method. For example, let's take up an example of a linear set of equations, the f. We can transform these into the Groebner basis, into the g. Here we see that the g is very simple form, and we can manipulate these simple equations for their answers. And the interesting property is that even if we change the basis, the solution set of both these equation sets remains the same. Now let's actually solve one polynomial using the Groebner basis. Let's consider there are three set of equations, the f1, f2 and f3. Consider I as the ideal set of equations, which was f1, f2 and f3. Now we'll put this into the Groebner basis method and we order those according to x, y, z in the descending order. And when we put this into the Groebner basis method, we get 4 equations which are generated by the Groebner method. And here we see G1 contains x, y and z variables, the G2 contains y and z, the G3 contains only y and z, and for G4 we get a univariate polynomial equation. Thus we can see that if we want the solution for z, we can calculate it from the 4th equation and we can back substitute it into the above G3, G2 and G1 and get the solutions for x, y's and z's. Now how do we apply it for the set of polynomial equations? We get it for the inverse kinematics. Now the steps as explained by Cy and Morgan as follows. Now the terms are first ordered by the total degree. That is, we order it according to z, y, x and t in the descending order. Now with total degree ordering, we can solve the Groebner basis G of the 7 equations we derived earlier. Now, after obtaining the Groebner base polynomial set, we choose one equation wherein we have its univariate in z and which has the lowest degree of the polynomial. Now this lowest degree of the polynomial gives the solution numbers for the general 6R mechanism. And once the roots for the z are found, we can use the back substitution method to find for the other x, y, z's, u's and all. Now if we compare the Groebner method with the Crane and Duffy method, the main difference would be we don't use the Sylvester method at all. We totally eliminated it. That's the major difference. And the advantages and disadvantages, Arima will tell you more.
Since we're short on time, I'll just kind of brush through them. We get only 16 solutions as opposed to Crane and Duffy's 32 equations. And there is no need to perform any mathematical manipulations. You don't have to apply any trigonometric identities. And since we don't use Sylvester's method, we basically get a set of polynomial equations, linear equations that we need to solve. And usually for this, we found out that if you use Groebner basis method, you get 72 equations and one of them will be a polynomial in z or something. And you can take that and back substitute it in all the other variables and you'll get all the 16 angles. And you can project it in the vector loop for the joint angles and joint lengths and stuff like that. And the disadvantages is that Groebner uses a lot of computational power because it's got 72 equations that it needs to solve. It took about 10-15 minutes on MATLAB. We use Mathematica, so it was running.
And we wait for 15 minutes.
Okay. Yeah, so that's about it. Thanks.
I think equal contributions amongst all 3 of those guys. So please repeat the questions that we posed to you. So you were inspired by a journal paper
Yes.
to do this. So you implemented that method in Mathematica, in MATLAB, and actually ran it?
Yes.
Okay.
If you can show you the painful
The 7 equations that we got from MATLAB, we've. So this is what we got from MATLAB after we kind of expanded it out. I mean, we used the simplify method and the simple method in MATLAB, and this is what it basically shoved out. So you can just basically chuck this into. So you can basically chuck this into. There's a function called Groebner basis that they've written, and you can put it in there, and it'll give you all the Groebner.
There's a
Groebner basis.
It's the function called Groebner base, and then you put in all your set of equations.
And all the
you
variables
close the brackets and you press enter.
You get all the Groebner basis, so that really helped us. We got 72 equations.
So presumably this is useful for all all sorts of other simultaneous equations.
Yeah.
Yeah.
And this can also be